Okay, afternoon. First announcement. There's no Friday quiz for today. And there would not be a Friday quiz for next week also. We'll have a Friday quiz after that in week 8. And that would be the final one for this quarter. Okay. Regarding Monday, Monday is a holiday next week. So we'll possibly have the Monday quiz on the Wednesday of next week, because that would be the first meeting for next week. Okay. So as far as the quizzes go, Friday quiz, not for week 6, not for week 7, but we'll have one for week 8. And then Monday quiz will most likely be on the Wednesday. Also, the problem number 2 from last Friday's quiz, when I discovered the error, I reported to Pearson and they accepted that and they made the change. Okay, so it was, if you remember, the second problem asked you to find values for VCEQ and ICQ, the Q point values for VCE. The system was accepting values for VE, not VCE. And hence it was marking it incorrect for everyone. Okay. So Pearson has informed me that they made the change on there. And I'll also go ahead and make the change in the credit for all the students. Okay, so it will not affect your grades. That's what I'm trying to say. All right. Okay. Let's look into logic design. So we stopped here last class and we were talking about implementing this equation, okay, in with logic gates. So this this design is known as combination logic design because we're taking a combination of logic gates and implementing for a specific function. In this example, our function is, well, f is the output, and our function comprises of 5 different inputs: A, B, C, D, and E. A, B, C, D, and E. Now, if mathematically, if you take a look at this equation, what do you see? How would you begin solving this equation? If we wish to implement this in logic gates, where would we begin? We would begin with the last mathematical function that we need to perform. Okay. So if you were trying to solve this equation, what is the last mathematical step? Addition, subtraction, multiplication, division. What operation would be performed the last at the very end? I heard addition. I see some nods. Yeah, addition would be the last one. Logically, we would need to implement the OR function. So I can break this down. I can break this down into 3 inputs. I can say this is V1. I can say this is V2. And let's say this is V3. And they're all going to be logically added up, logical addition, right? So that would require an OR gate, right? Require, to be more specific, it would require a 3-input OR gate. 3-input OR gate. Make sense? Right? V1, V2, V3, and then all summed up at the end is a 3-input OR gate. Now, let's take V2 first. V2 is the most straightforward. We have 3 inputs, A, B, C, and A and B and C. So it requires a 3-input AND gate. Does everyone see that? Let's draw this out here. So A, B, and C. And the output here is ABC. Right, let's take a pause while you write it down or note it down. Make sense so far? Right? If you're implementing this logic, we would always begin at the last mathematical step. The last mathematical step would be addition, hence the OR gate at the very end. Right? OR gate at the very end. And we have 3 inputs. We broke down the function in 3 inputs. Then I'm taking the easiest one. The easiest one is ABC. Simply an AND gate, a 3-input AND gate. So V2 is done. V2 is done. What's the next easiest? I would say V1. V1 is A, B, C, but it's A, B not C. So it's again a 3-input AND gate, but B is inverted. So all I'm going to do is I'm going to pull a wire from here, and I'm going to invert. And then you'll again have a 3-input AND gate. It's B, and that's A, and that's, oh, that's not A. A needs to stop right here. We can show a connection by drawing a node. The absence of a dot in there means there's no connection. If there's a dot in there, it indicates a node, it indicates a connection. That's how we are showing those lines. Okay. So 3-input AND gate in the middle is V2, it's A and B and C. And then 3-input AND gate at the top, A, B naught, and C. And then that is fed into our OR gate. Done with V1 and V2. So far, so good. What is required for V3? What do you think for V3? Right? The last possible operation inside V3 is the AND. And then inside, we'd have 2 OR gates. Let's take a pause and think over that. Make sense? All right, let's do an AND gate here. This would be a 2-input AND gate. And here the output should be C plus D and D naught plus E. Okay. So I'd have a OR gate here to do summation of C and D, the output of which goes into the AND gate. And this is C plus D. That's C, and that's D. And then we have D naught plus E. And so we take D, feed it to an inverter, which goes into the OR gate, and that's it. Let's take a pause. Let me know if you have questions. Does the procedure make sense? Do the steps make sense? How many gates do you count in there? How many total gates do we need? Anyone? 1, 2, 3, 4, 5, 6, 7, 8. Total of 8 gates. Yes. Yes. So we have to count all of those. Yeah. Oftentimes, as we saw in the previous class, we would take a NAND gate or a NOR gate, and we'd create an inverter using those gates. So in real life, if you were implementing this logic, we'd have a bunch of like NAND gates, and we just implement using this logic. Again, if we had this equation, we had this function f you're trying to implement at its most basic, we would require these many gates. So logic design would basically entail how we can more efficiently use the resources at our disposal, right? So we can try to reduce this equation mathematically first, so that the number of gates that are required would be less, or at least a more efficient implementation of this equation. So if we take this equation, we can try and reduce it as much as possible to obtain lower number of quantities in our function. Okay. So F is equal to ABC, A B naught C plus ABC plus C plus D and D naught plus E. So first thing I'm going to do is I'm going to expand the last two quantities, which is V3. So we get C D naught plus D naught plus DE. Okay. C D naught plus D naught plus DE. If you have an input and you multiply it with this inverted value, what do you get? So D naught would go to 0. Take a look. If D is 0, D naught is 1. 0 times 1 would give you a 0. If D is 1, D naught would be 0. Again, 1 times 0 would give you 0. So the product of D and D naught would go to 0. That's one quantity eliminated. Yes. Yeah, you're right. CE. So C D naught, D naught plus C D naught in CE. Yes, that should have been the second quantity. Does that make sense to everyone? D naught goes to 0. So one quantity is eliminated. Then what other quantity is common? What other quantity is common? Or the most common in all the terms? C, right? So C is present in the first, second, third, and the last. So if I take C out, I could write F is equal to C AB naught plus AB plus D naught plus DE. Actually, that would remain external. E plus DE. All right, let's see. AB naught C plus ABC plus C D naught plus E plus DE. Okay. So far, so good. There is one more thing you can do. A is common between the first two quantities inside, and so I can make a further reduction. If I take A outside, I can get B naught plus B. And B naught plus B reduces to 1. Okay. B naught plus B reduces to 1. If B is 0, B naught is 1. So 0 plus 1 gives you 1. If B is 1, B naught is 0. And then again, 0 plus 1 gives you 1. So the sum of the input with its inverted put would give you 1, and the product would give you 0. So then I can write this expression as F is equal to C and A plus D naught plus E plus DE. Now let's see how many gates would be required for this. We have one big OR gate, one AND gate, a 2 input OR gate, one AND gate, and a NOT gate for D. 1, 2, 3, 4, 5. 5 gates versus 8. Okay. Let's take a pause and let me know if you have any questions. Do the steps make sense? The reduction of the equation is simply, it follows the same rules as mathematics. Okay, the same mathematical rules that we use to solve any equation. And so depending on the function, we can take that equation, we can reduce it to produce a more efficient implementation. Efficiency simply means using the resources that we have on hand. Right? If we have an unlimited number of gates, we can implement it using whatever we want. But if we are limited in our choices, then we need to redo our function according to what we have. All right. Okay, so this is all combination logic design, meaning we take different combinations of our logic gates to implement a function. Then we have something known as sequential design, so sequential logic. In sequential logic, we have circuits that are implemented with logic gates, but they are capable of storing information. Okay, so they're capable of storing information. Hence, they are known as memory circuits. The combinational circuits would not store any information, so they would be known as memoryless, no memory. Okay, no memory. Now, in sequential logic, everything takes place in a sequence. But we need something to keep everything working in synchronicity. And hence, we apply something known as a clock signal, which is shown right here. This is a clock signal. Clock signal is a rectangular pulse or a square wave with simply defined regions of logic high and logic low, ones and zeros. Okay, alternating waveform of ones and zeros. It has any AC signal. This would be 1 cycle. And if this was 1 second, we would say the frequency was 1 hertz. Right? How many times in a second it changes? So ones and zeros. So clock signal keeps everything in sync. And based on the kind of circuit, we can have synchronous circuits or we can have asynchronous circuits. Okay. But a clock signal would be required. What is the frequency of our power outlet? Should I go back and change your points on the quiz? What's the frequency of the power outlet? 60 hertz. Shouldn't take this long to answer. Not as an engineer, as a general population. This is a general knowledge question. What is the frequency of the power outlet is a general knowledge question. Doesn't require an engineer's degree. 60 cycles. Anyway, the point we're trying to make is the voltage goes from 0 to a positive value back to 0, sine wave. So we have 1 half cycle. Then it goes from 0 to a negative value and comes back up to 0, negative half cycle. 1 full cycle is a positive peak and a negative peak. And the number of times it goes through a positive and negative peak in 1 second is the frequency of the waveform. So in North America, the voltage at the power outlet goes to a positive and a negative peak 60 times in 1 second. That fast. But 60 hertz is a very, 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 very low frequency. My ears probably can't even listen or distinguish between those sounds. Okay, 60 hertz is a very low frequency. As a real life example, if you think about the CPUs in your mobile phones, in your tablets, in your desktops, in your laptops, the frequency of those CPUs is 1 gigahertz, 2 gigahertz, 3 gigahertz, and probably even larger than that. That frequency, 1 gigahertz frequency of the CPU, is the frequency of the clock signal that is running your entire system. It's keeping everything in sync. And so every time a process occurs, it occurs in a sequence and occurs that fast. So if you have a cell phone and it says CPU of like 2 gigahertz processing frequency, that's the clock signal frequency that's running things. It's performing that many operations in 1 second. Okay. Going back to the earlier slide of unit prefix, how much is 1 giga? This is an engineering question. It'll show up on the final exam. Yeah. Giga is tera, yes. Not tera, sorry. Giga is a billion. Remember 1 million seconds and 1 billion seconds? Anyway, so the first circuit that we're going to look at in sequential logic is a flip-flop known as SR. Now, when I hear the term flip-flop, it brings to mind the Caribbean or Hawaii. But these are not as, well, as an engineer, they are fun, but not generally speaking. The reason they are called flip-flops is because the output of the circuit changes or flip-flops between 0 and 1, depending on what your input is. Hence a flip-flop. And to begin explanation of flip-flops, let's take a look at a very simple circuit where you have 2 inverter gates, and the output of each gate is fed back as input to the other. Okay, the output of the gate is fed back as input to the other. So if this was A and this was B, output of A is labeled as Q, and the output of B is Q naught, simply the opposite. So to begin analysis, we would assume a state. If we assume Q is equal to 1, what is the output of B? If Q is 1, what is B? Out. 0. And if Q is 0, what is B out? 1. But if B out is 0, then the input to A is 0. So Q is 1. So it stays consistent. Yeah, let's take a pause. If Q is 1, B out is 0. If B out is 0, let me write it down there. If B out is 0, then A in is equal to 0. Hence A out or Q is equal to 1. And if A out is 1, B in is 1, which is the same as the first assumption. So B out is equal to 0. System is stable. There is no changing anything. And if Q is equal to 0, B out is equal to 1. That means A in is equal to 1. A out is equal to 0. Make sense? Inverted output going back as input to the other gate. But this gate sorry, this circuit is not very useful because there is no control. We cannot apply any input externally. We cannot control it, right? But this is just to show how the output being fed back into the input can create a stable state for the circuit to store the result. Right? The result is stored in there. It's not changing. But now, if we create a circuit using NOR gates, NOR gates, and we feed the output back to the input of the other gate, now we have something. Let's first write out the truth table for a NOR gate. In a NOR gate, if you have two inputs, X and Y, zero, 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 one, 1, 0, 1, 1. The output of a NOR gate goes high only when both inputs are low, right? 0 plus 0 gives you 0. Inverted output, 1. For all other combinations, the output is 0. 0 plus 1 gives you 1. Inverted output, 0. 1 plus 0, 0. And 1 plus 1 also gives you 0. The output of a NOR gate goes high only when both inputs are 0. So if we use that, we can begin analysis. This flip-flop comprises of two NOR gates. The output is fed back as input or as fed back as one of the inputs. The other two inputs are labeled as R and S. The R stands for reset. The S stands for set. So S stands for set, and R stands for reset. Okay. Set, as the name suggests, would set the output to 1. Output goes 1. And if reset is high, then the output goes to 0. Output here in any gate is referred to as Q. Output for any gate for any flip-flop is referred to as Q. Q is the output always. If you take a look at your lab kits, your labs 6, 7, and 8, you're going to use logic chips in there. And each one of those, there are inputs and outputs. All the outputs are labeled as Q. And for convenience, at the same time, we also have output Q naught. Okay, so that would be the secondary output. That would be the inverted of Q. But when you say output of a flip-flop, we always refer to Q. Generically, we might say, okay, we're going to take the output from Q naught, but technically, when we are referring to the output of a flip-flop, we always say output is Q. Okay, and this is going to be important. When set is high, means set is 1, output Q goes to 1. When reset is going to 1, then output Q goes to 0. Hence the names set and reset. Set means output Q goes to 1. Reset means output Q goes to 0. Okay. Keep this in mind and kind of commit it to memory. For all of the flip-flops that are following, we follow the same logic convention. All right, let me know if you have any questions. All good? Okay, let's analyze the circuit then. Let's assume let's assume that S and R are both set to 0. Okay, let's assume that S and R are both set to 0. That's the first one. So RS is equal to 0. That's the first state. First state. Input to the flip-flop are 0 and 0. How do we begin analysis? Well, for 0 and 0, let's assume that Q is equal to 1. R and S, input to the flip-flops, are 0 and 0. Let's assume that output Q is equal to 1. Okay. If Q is equal to 1, what can we say about Q naught? If Q is 1, what is Q naught? 0. So we can begin our analysis from this state. Now, let's turn our attention up there in the diagram. S is 0, R is 0, Q is 1, Q naught is 0. Q is fed back to input of B, so it's 1 here, and then 0 here. Look at the truth table for the NOR gate. NOR gate B, inputs are 1 and 0. What is the output? What's the output? Look at this table. Output of gate B, zero. Now, did the output change? R and S are both 0. Our initial assumption is that Q is 1 and Q naught is 0. The result of the analysis is that Q naught stays at 0. That 0 is fed back to A, and output of A stays at 1. Meaning Q remains at 1. Makes sense? Right? Now, if you assume Q is 0, therefore Q naught is 1. Q is 0, Q naught is 1. What happens then? If Q is 0, again, we're up here on the diagram. If Q is 0 and Q naught is 1, Q naught is fed into A, Q is fed into B. Output of A goes to 0. Output of B goes to 1, which again is the same result as our assumption. So if Q is 0 and Q naught is 1, the result is that Q is 0 and Q naught is 1. The sum of this analysis is that when R and S are both equal to 0, the output does not change. If the output Q was 1, it will remain as 1. If the output Q was 0, it will remain 0. And hence, we say output Q for R equal to 0 and S equal to 0 is Q n minus 1, where n represents the current state, N minus 1 represents the previous state, and N plus 1 represents the next or the future state. So again, output Q for the first input, meaning R and S both are 0, output Q does not change. It remains what the previous output was. If the previous output was 1, it will remain as 1. If the previous output was 0, it will remain 0. And hence, or thus, we can say the circuits have memory. They have stored information. If the input is 0, 0, the output does not change. Output remains the same. All right, let's take a pause and let me know if you have any questions. Does that make sense? This is all, as I said, we will go in a very different direction when we begin chapter 4, logic circuits. So it might take some time to sink in, but do you have any questions at this moment? Did the process and the steps make sense? I can understand that you need to take time and analyze it again at your own time outside of class, but did the steps make sense? Okay. Let's then quickly look at what happens when R is 0 and S is 1. Okay. So if R goes to 0 and S goes to 1, we have NOT gates A and B. NOR gates A and B, right? The only way that the output of a NOR gate goes high is if both inputs are 0, right? 0, 0 gives you 1. For all other combinations, it is 0. So in a RS flip-flop, if R is equal to 0 and S is equal to 1, this NOT gate A, this NOR gate A would have a high output, meaning Q would be equal to 1 only when this input, second input of A is 0. The second input of A comes from Q naught. If Q is 1, Q naught must be 0. And if Q is 1, then input of B is 1. So the output of B must go to 0. So irrespective of what the previous state was, if R goes to 0, the output Q, if R goes to, I'm confusing myself. If R goes to 0, output of Q goes to 1. Okay. So Q naught would be equal to 0 here. The only way output of a NOR gate goes to high is if both inputs are 0. Okay. So if R is 0 and S is equal to 1, Q goes to 1. Again, if R is 0 and S is 1, output Q would be 1, and output 1 is fed back to gate number B. Because both inputs of gate number B are 1, output Q naught will remain at 0. That 0 is fed back into A. Both inputs of A are 0, 0. So output of A, which is Q, goes to 1, which again then cycles through. All right, let's take a pause. Let me know if you have any questions. If R goes to 0, S goes to 1, output is 1, which is this state. Similarly, if R goes to 1, S goes to 0, then the output flips. Q becomes 0, Q bar goes to 1. Hence, set reset. If set goes 1, Q goes 1. If R reset goes 1, then Q goes to 0. Okay. And you can, again, review this after class as soon as you can. I'll post the video as soon as I can after class. But then you can analyze and think about it at your own time. Okay. One other thing is, what happens when R and S are both equal to 1? If R and S are both equal to 1, then the output is unpredictable. It could be a 0, it could be a 1. We don't know. Hence, we say that that state is not permitted or it's not allowed. Because the output is unpredictable. Okay. If both inputs to the flip-flop R and S are high, meaning equal to 1, then we cannot predict what the output would be. And that's why we call it a state that is not permitted. It's a state that is not allowed. Okay. We cannot predict what the output would be. So the system would be designed in a way that that combination of input is not allowed. Okay. And there's something else I wanted to do, which is the timing diagram after this. We have only about 1 minute left. So if you must leave, feel free to leave. I'm just going to continue after 2 o'clock. Timing diagram essentially is like a graphical representation in a way to determine the answer graphically. Okay. Everything is plotted with respect to time. Hence, it is known as a timing diagram. And we break down the inputs and the outputs in chunks of time. In this case, we are breaking it down between 3, 4, 5, 6, 11, 7, 8, 9, and 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We look at the inputs, then you look at the truth table, and you can draw the output graphically. So here, my S input and my R input are displayed graphically. I'm going to simply write out the logic level based on the waveform. So my set input is 1, 1, 0, 0, 0, 0, 0, 3, 4, 5, 6, 7, 1, 0, 1, and then 0, 0, 0, 0, so on and so forth. And my reset input is 0, 0, 0, 1, 0, 1, and 0, 0, 0, 0, and then 1, 1, 1 continues for 11. Between the time period of 0 and 1, my reset input is 0, 1, and 0 should give me logic high or 1. 1 and 0 should again give me a logic high or 1. Between 2 and 3, both inputs go to 0, 0, but the output does not change. Output remains the same. So Qn minus 1, output remains 1 until 3. Then between 3 and 4, output goes low because my reset input goes high. So if reset goes high, output goes low. Then 0, 0, output remains Qn minus 1 does not change. In this case, previous output was 0. So output again remains 0 between 4 and 5. Then between 5 and 6, reset is still high. So 0. And again 0, 0. So Qn minus 1 between 6 and 7. And then between 7 and 8, output goes high. So output, actually, that's not the case. 7 and 8, output goes high. Then it's again 0, 0. So it's again Qn minus 1. The previous state remains high. Between 9 and 10, it's again high. So it remains high. 1 and 0. And then between 10 and 11, it's 0, 0. It remains previous state, which is high. And then after 11, my reset input goes high. And so output goes to 0. And it remains 0 from that point on. Okay. And that's how you would graphically solve for any input. That is known as a timing diagram. Sorry for going over time. Please review the video. Please review the lecture. There's a lot to think about and understand. So if you have any questions, reach out to me. I will be available over the weekend, not traveling or doing any other thing except chores. All right. So have a good weekend and let me know or reach out if you have any questions.